this problem. We got Maclaurin series, we got radius of convergence, integral test, limit comparison test, just finding that next term to find the error. It's a loaded up problem there. There's all my work, all my answers kind of right there. Let's kind of walk through it. The very first part, all right, it says we have this Maclaurin series. It gives us this nice power series. And then it says state the conditions necessary for the integral test to determine if this test converges or diverges. Now, the integral test, we didn't spend so much time on this, but you might want to kind of read through your series test here, the converge and diverge, like through the actual book there. It says for the integral test to apply, your function has to be positive, continuous, and decreasing. All right, so those three things, positive, continuous, and decreasing. And then if you think about this 1 over e to the x, that 1 over e to the x, that is positive, right? Think about 1 over e to the second, 1 over e to the third. That's like 1 over 2.72 to a power. So that's going to be a positive series. It's going to keep getting smaller and smaller, just like 1/2 to the x or 1/3 to the x. Think about that graph. And it is continuous. Okay, so I just wrote down for the conditions to use the integral test, positive, decreasing, and continuous over that given interval from 0 to infinity. And then we're supposed to use the integral test to show that this series converges. Now we know that's a geometric series as well, but they told us to use the integral test. So remember, use the integral test. Be very careful with your notation. I'm going to do the limit as b approaches infinity from the integral from 0 to b of that. That's really e to the negative x. So your u is that power. The du is equal to -1. So remember, when you integrate e to the u, you get e to the u. But then if your u was that power and your du was -1, you got to balance that with the negative right there. I got rid of my negative exponent. You have a definite integral, plug in the top minus plug in the bottom number. And then we're going to do limits that b approaches infinity. So since we get 1 over infinity, that's going to go to 0. E to the 0 is 1. So we get 1 for that. So we get a finite answer for that integral. So that means that particular series converges by the integral test. All right. Part B says use a limit comparison test. And then we want to, with this, so it kind of gave us the comparison series. So we already know that that's our comparison series, and we already know that that comparison series converges. Okay, so we don't have to do that extra part. We already have that part done, but we got to see if this series converges absolutely. Now, if it does that absolute convergence, we got to do the absolute value of that series right there. Okay, so it tells us to use a limit comparison test, and you're doing this absolutely thing. So if I were to do the absolute value of this series, that means the absolute value just takes that -1 to the end notation away. So I could start out this limit comparison test and I can use the absolute value notation, or I can just realize the absolute value notation is making that -1 to the end disappear, just like when we did our ratio test when we first learned it there. It's just going to make that disappear. And so kind of use it. So I read through the rubric and stuff like that. So I'm going to use a limit comparison test. Remember what we do? We do the limits and approaches infinity of the original one over the comparison one that they told us to use. So I could throw that one in there and use the absolute value bars, or I can just go straight to that. So they did have on the rubric that there's more than one way to illustrate the use of the absolute value bars. They said if you just went straight to the positive of that series, that's utilizing correctly the absolute value bars right there. So that's what I would do there. Or you could put them in just like that. So either or is okay, but I'm going to do limit comparison tests and say, tell me they're doing that. And I got to use these absolute values just because of that converges absolutely type of deal right there. So if you need to rewatch that absolute or conditional convergence there, go ahead and do that. But I did my limit comparison test, got the original over the comparison one, multiplied by the reciprocal. And then I had this e to the n over 2 to the n plus 3. Now that's like an infinity over infinity type. I can kind of know like just that this answer is going to be 1/2 right there. I can go to that. But if I did L'Hopital's rule, the derivative of e to the power is e to the power. And then the 2 e to the power is 2 e to that power. I applied L'Hopital's rule since I had infinity over infinity. The derivative of that was 0. Those EVNs cancel out. And then I had the 1/2 there. But you can just, as long as you got this set up there good, and if you could know that that's going to be 1/2 right there, then you're good. Now that is a finite positive number, which means both series are going to do the same thing. So since we already have that this comparison one converged by the integral test, that means that this one is also going to converge by that limit comparison test, because that's what we're checking. When I ignore that -1 to the notation, I'm checking the absolute value of that. And so if the absolute value of that thing converges, then that means that that series that's in question. So they talked about that series that's in question converges absolutely right there. They did mention on the rubric, if you just put the series converges absolutely and didn't mention which series, because they got this series, it's like there's a couple of different kinds of series in there. They just mentioned if you just wrote down the series converges absolutely, they didn't give you full credit for that. You had to mention G of 1 converges absolutely, or that series converges absolutely. So that's the nuts and bolts part. I think we kind of figure stuff out there, but let's just try to get a little bit better with the technicalities right there. So if you just want to write a little bit more just to be safe, then we're going to be good there. All right, now once I got to letter C just says find the radius of convergence. Now the good news is when you see radius of convergence, it's not the interval of convergence. So you're going to approach it the same way, but you don't have to do as much work. Interval convergence, we would have to check the endpoints and stuff like that there. So radius of convergence, we're going to need to do the ratio test with this guy right here. Okay, so I'm gonna do the ratio test with that. So I'm gonna do limits and approach to infinity. I need to put the absolute value bars in there, and then I'm gonna replace all the n's with an n plus 1. So I did that, and then we're gonna divide it by that original, which means we multiply it by the reciprocal of that. And then the fact that I got the absolute value bars in there, it just makes all that negative stuff go away. So that just goes away. And then remember, what makes a ratio test converge is if that limit answer is less than 1. So we're going to squeeze that in there. And then I just canceled out the negative stuff because I have the absolute value bars in there. That x to the n plus 1, I rewrote that as x to the n times x to the first. The x to the n is canceled. And then so I had the x to the first carried down, that carried down, this carried down. And now what we could do is pull out the x, and I still got to have the absolute value bars, remember. And then you got the limits and approaches infinity of all the stuff with the n's there. And then what I did is I did L'Hopital's rule. So this is like infinity over infinity. I did the derivative of the top, did the derivative of the bottom. And then I rewrote that the 2's canceled. I rewrote that as e to the n times e to the first. The e to the n's canceled out, and I just had 1 over e. So the limit of a constant is just that constant. And so you have the absolute value of x times this is less than 1. And then all you got to do is multiply both sides by the e. So when it's in that format, like the absolute value of x is less than that radius of convergence right there, that's going to be the radius of convergence. So that's what I'm trying to match. So I just multiply by the e, boom, that's my radius of convergence. Now, had it said the interval of convergence, then I do the less than sandwich, then I got to check the endpoints, and this is a lot more work. But this problem is already loaded up as it is. So I think they did that intentionally for us to be able to just stop right there. There's our radius of convergence. Now, once we get to that point, even if you had trouble with parts B and part C, part A we should have pretty easily there. Part B hopefully makes a little bit more sense. Part C, we have this similar to our power series video with the BC extra video lectures that we practiced right there. So I think we could be successful with that one as well. But part D is actually a really easy part of the problem. Even if you had a little bit of issues or time issues with either B or C, you can get part D all by yourself. So I think when I initially worked this out, I kind of skipped over part B a little bit because I felt a little more comfortable with C and D. And then I went back and I kind of just was careful with that absolute convergence type of thing. But remember, if you have an alternating series, the alternating series error bound, you just got to look at the next term in that sequence right there. So technically, this is an alternating series whose terms decrease in absolute value to 0. But all you got to do is find this. If you just find the next term, you're going to be good. So they told us the first 2 terms were used to approximate it. G of 1, and then it says use the alternating series bound. So if you use the first 2 terms already, it started at n equals 0. So n equals 0 was the first term, n equals 1 was the second term. So that means n equals 2 will be the third term. And so you just do the absolute value of that. So technically the error is less than or equal to, that's the maximum that is going to be. So you just got to find the next term in that sequence there. So you do the absolute value of it. I just took n equals 2 and I plugged that in right there. Plugged in n equals 2, did the absolute value of it, boom, and I got that right there. So technically, that's the maximum that error is going to be. It might be less than that, but as long as this part was just, they said, as long as you can get this, then you're good. We got that. So just find the next term in that pattern right there. So if they said the first 2 terms, just go to that third term, and then just be careful with that there. So that was a tough problem. There's a lot of stuff in there, a lot of loaded up stuff in there, but everything in there we can handle right there. So just try to keep studying with that stuff, with the language there, and try and get a little bit better with the tougher parts of that were good. And then just make sure that if you are having trouble with a couple of the tougher parts there, keep going, because look how simple this was. Look how similar this was to our video notes and stuff like that. All right. All right. Thank you. The Great Lakes.